in which sense it could be done in a better way. Just a remark, then we will discuss it in a more detailed way, and I hope that young participants will say openly their opinion. For instance, Professor Berdichevsky simply ended before starting, in the sense that after having discussed all preliminary tools which are necessary for discussing some problems, then time ended. In my opinion, one weak point of this wonderful organization, I mean, CISM is very well done, but the weak point of having too many people talking, this is, I think, for avoiding that somebody believes himself to be a genius, and so he is allowed to talk and to teach for a long time. So this idea of having too many speakers, in my opinion, is not very good. But now I tell you the consequences of this consideration on my own talk, and the reason for which now I show you some simple integration by parts. I could do this in H1 space, and I could introduce Banach spaces, Fréchet derivatives, and in my opinion it could be very healthy. However, mathematics of other people is always considered very complicated, while your own mathematics is easy. This is a standard rule when you hear people talking about this subject. So I want to ask, my aim is now to show you that second gradient theories cannot be formulated in the standard Cauchy way, at least not easily. While if you get a variational approach, second gradient theories can very easily be formulated. I will show you quickly, and I will hide some details of mathematical type, but I will underline where difficulties are. I will show you how contact action through a Cauchy cut can be estimated, can be found. I mean, I will show you which is the structure of Cauchy interaction by means of contact action, by means of integration by parts. In particular, I will show you how you can rediscover Cauchy interaction more easily than using famous tetrahedron argument. You need a simple integration by parts. And I will tell you, but I will try to keep not too polemic. I will tell you how Cosserat brothers already used a principle of virtual powers, which I don't know why nowadays somebody calls non-standard. And unfortunately Professor Berdichevsky is not here, but he would jump looking this, while he would say, I'm a good boy here. Okay. There are people who believe that notation is everything. So as Cosserat brother used, instead of tensors, matrices, first row A, B, C, second row D, E, F, third row H, I, L, then this is not the principle of virtual works. While if you use an absolute elegant notation, then it is non-standard principle of virtual works. You know, notation is useful. very powerful. But this is the beef of the argument, and this is Lagrangian style. Okay? So I would say that I have a field psi. Grad psi for me is a quick way for avoiding to write d psi over dx, d psi over dy, d psi over d zeta. Okay? Yeah? No, this is nothing. This is a mathematical operator. Then we will apply to particular case. You have a volume V, remark, it is fixed. This is for answering Gilles' question. So you have a given volume, a region in R3, you have fields defined there, you have gradient of this field, second gradient of this field, and then you estimate integral of W psi grad psi, second gradient of psi, and you try to, if we want to be elegant, we try to estimate Frechet derivative of this, but if you want to talk about Frechet derivative, then you have to say which Banach space you have chosen for psi's. Lagrange was not doing this. He didn't know about Banach spaces. So let us try to follow the main idea of Lagrange. Then we formulate maybe in a more complicated way. So we change a little bit psi, and I jumped some passages. It's clear that this is, you can use this, you can get the first equality simply remembering Taylor's expansion for the function W. Okay? So I simply want to show a formal structure of a Frechet derivative of a functional. Okay? Okay. Then, when you get this, remark delta with red, because I want to underline that delta psi is a different object with respect to psi. So psi is a field which will become the stationary field for this functional. Delta psi is the, to be elegant, the tangent vector, I mean the small variation of this psi. Okay, then let us consider this animal. Okay, maybe we should stop a little bit following Lagrange. If you have an arbitrary variation delta psi, then unfortunately grad delta psi is not arbitrary. So you are in troubles if you leave the equation in this formula, unless you are clever enough and you manage to integrate by parts. At the end, you will get a formula in which only delta psi appears. However, a serious mathematician could now start telling me that, okay, this is Berdichevsky. By the way, joking yesterday, we said that we will record our lectures, we will send them to Berdichevsky, he will record questions, then we will answer questions, and we will send you all the movie, okay? So we'll enjoy again our discussions. I think they are useful. Now you have that dw over d psi I delta psi I summation over I and j is implicitly indicated. Then you can integrate by parts in the sense, if you have divergence of all these animals, you apply Leibniz rule, then you get this animal, which being on the right side of the equation is with minus, plus this animal. Okay, now we could stop here hours. which is the set of functions for which you can estimate divergences, which is the regularity of the domain where this next trick I'm going to do can be done. Of course, this is a very difficult topic, but we go ahead. We apply divergence theorem here, okay, and we get flux of something. You have normal. In this something, you get delta psi I, okay? We are happy because this is independent, right? And this animal can be interpreted as something per unit area, which is corresponding to the flux of a quantity, which depending on our W, and depending if it is Eulerian, Lagrangian, I mean, which is the frame where you study these things, will have a physical interpretation. Okay? What I'm telling you is rather standard. And you have minus divergence of something, okay, in the bulk. So if you now interpret this as deformation energy, and you are careful with the normals, okay, because this normal, if this is a deformation energy, if V is a space Lagrange coordinates for a solid, so you are in the configuration reference, then this normal is a material normal. Okay, so in a sense, this flux is what we call Piola-Kirchhoff stress. Okay, which is rather easy if you start with energy, but if you use the flux Eulerian, becomes a nightmare. Okay, if you read the book of Cosserat brothers, they used for teaching at l'Université de Toulouse at the end of the 19th century, you find this deduction exactly as it is for third-year students. There is nothing complicated in this. Okay, of course, if you want to do it in H1, then you need more mathematical tools, but this is not what we want to do now. Okay, so which are contact forces? Contact forces are something which depends linearly on the normal of Cauchy-Cat, okay? And we don't need to painfully look for energy, say it is hyperelastic or not. You immediately get dW over d psi, and psi is the gradient of psi. If psi I is displacement, you can easily reconduct this to deformation. Also the W, the derivative of W with respect to the deformation gradient. But you need to tell that W depends only on deformation. In the book of Landau, you find this as a general frame for attacking every physical problem with a variational precision. Okay. Now, I do not know why, for a long while, everybody was victim of Cauchy interpretation of this result. Because Cauchy, instead of starting from a variational principle, looked at the final conditions and formulated so-called, God forgives him, Cauchy postulate, contact action depend only on the normal. Why? Physical intuition. This is what has been said very often. integration by parts. This is the right answer in my opinion. Okay. Then he builds balance of forces, and then with a nice argument having, you know, Cauchy uses the principle of virtual powers for a family of tetrahedra shrinking to zero, and he gets the existence of a linear function of the normal. So I remind you, contact actions for Cauchy depend only on the normal. Then he proves that they depend linearly on the normal, using balance of force. Okay? Now, forget all this. You know, Cauchy. What? No.
I want to play.
No.
But I just want to before we want. Cauchy's idea, but there's also the idea that the stress might not come from an energy.
Yeah.
So in which case, okay?
Yes, but you know, I am afraid I've read that, of course, this is an interesting topic, which deserves to be studied. Okay, you can attack the problem with Rayleigh-Hamilton trick, so you always need this. But I agree with you, this is a point. But I want to underline the other thing. I want to underline that for sure, because les comptes rendus de l'Académie des Sciences are not lost like ancient Greek books. So you can track ideas. And the track of ideas was this one, not another. Then somebody said, I want something which is not depending directly on energy. So I try to do a better job. Okay? But when you try to do this, you tie your hands. I will tell you how. If instead of having first gradient of psi, you have second gradient of psi, this term must be added. Unfortunately, the blackboard is not big enough, so I will need to copy another page of calculations later, but I will erase this. So you get, this is standard, but look, you have two gradients here. So you start with the first integration by parts. This animal has exactly the same structure of the one we have already studied. So to show you that I have learned Fortran, go to 1, and you know, you restart then, and look, you discover a very interesting stuff. You not only have this Cauchy stress, but you also have another term of Cauchy stress coming from an independent third order tensor, this one. Okay? So the force per unit area do not depend only on one second order tensor, but it depends at least, but we will discover that there is another piece, it depends at least on the divergence of a third order tensor. Everybody who studied beam theory of plate theory knows this, because plate theories and beam theories are second gradient theories somehow, because in the energy you have second gradients of displacement. But now let us focus on this animal. This animal is this one, okay? You integrate, you call this tau I h, because you integrate by parts, so you get that this volume integral becomes a surface integral. So I knew maybe Gilles did not know Professor Bredisiewski. So I knew that it was very dangerous, and I want to live quietly, to say that you need a volume with finite perimeter in order to perform this integration. Okay, but Gilles did not know, maybe. Okay? So now you get this, and now I am in serious troubles, because I need differential geometry for surfaces. Because for going ahead now, and for this reason, I abandon a notation which Victor likes for using another notation which, being perfectly equivalent, allows me to do a trick. You know, divergence theorem holds also for surfaces. If you have surface fields, you can estimate surface divergence of these fields, and this surface divergence integrated over the surface gives you a flux along the border of this surface, flux estimated with the normals of the curves in the tangent plane of the surface. So you need Gauss differential geometry at least for proceeding these calculations. Okay? So I decompose, because I want to do this integration by parts on the surface. I decompose grad. What is grad? Grad is a linear map between a tangent space to another tangent space. It maps the variation of independent variables in one direction to the variation of the dependent variable in the arrival space, in the codomain. Okay. I decompose this linear map in, let us start from the other side, grad delta psi n, which is the normal derivative of delta psi, tensor n. Then I subtract to grad delta psi this animal, and I call what remains surface gradient. Up to now it is only a definition. What is painful? Now I pull Sergei's leg in absence of Victor. We need to prove Ostrogradsky-Poincaré theorem for this grad. Because you have a surface, you know, Poincaré showed this with chains and borders of chains, something very elegant, which was my exam for being allowed to talk with Professor Di Carlo when I had your age. You have hyper surfaces of n dimension, and you have border of these hyper surfaces, and these borders have a lower dimension. In this case, we have a surface, and the border of a surface is a curve. Okay? So, but before going ahead, remark that this animal is complete in the sense that in your domain, this is very important now, you have your V. What you can do, you can have a test function which is different from 0 here and 0 outside. There is an elegant theorem due to Lagrange in the first version which tells you that if you have volume integral of something times an arbitrary delta psi being delta psi suitably regular, then this animal is 0. Okay? So if you have a test function concentrated in the neighborhood of a given point, you use this test function and you get bulk equation. If you are on the border, on the boundary, you are good enough, you do this with half a sphere, okay, or with a neighborhood only in the bulk, but you can also have a function whose normal derivative at the boundary is arbitrary and which is vanishing very close to this. So when applying our variational principle, that is, a first variation of something equals 0, you get as many equations, as many independent test functions you have in your hands. And for this reason, I always, now I'm becoming old, repeat la cinématique d'abord. If you do not know which can be varied, you will never find the equations. So this normal derivative can be varied arbitrarily. Okay? So you will get wonderful boundary conditions. You get these Cauchy boundary conditions on the border, but you will get extra boundary conditions. The wonderful feature of second gradient theories or variational principles, and the particular case second gradient theories, is that you get immediately boundary conditions. And these boundary conditions, being derived by an energy, if your energy is well behaving, are surely giving you well posed problems. But you know, I'm not telling you that I have invented this or somebody here invented this. You find this in the book of Professor Cossera for his students, third year, at the end of 19th century. This is an idea. Maybe Sergei will tell you that in Russia they were doing it before, and we will agree. Okay. Now, let us handle this animal, okay? Because this animal will give you another astonishing feature. You will get a force per unit area which depends on curvature. So the gradient of normal. So Cauchy postulate actually is a constitutive assumption. Take this in mind. Why do we stop here at the second gradient? A choice. By the way, Gilles says that I'm crazy with French, but Schwarz, even if name is rather German, was French. There is a wonderful theorem due to Schwarz who tells you that the most general distribution, so the most general derivative of Frechet derivative of energy has a very particular form. So every distribution is made in this way. Sum integral V. Here you have A alpha. Alpha is the typical multi-index of distribution theory. And here have the alpha derivative of your test function. And this is between 0, 0, and you have a finite order of derivatives. So the most general power in continuum mechanics, as a particular case of this, is made in this way. So when you stop at the first gradient, you are making a constitutive assumption on the only true constitutive quantity which must be used for describing nature, the Lagrangian. Do you want a more complicated model? You can use second, third, fourth, nth gradient. Schwarz's theorem tells you that in this way you get every conceivable power Okay? So, stopping at the first gradient level means you limit to Cauchy continua. Stopping at the second gradient term, let me say this, even if this is not written, you stop at Germain continua. Okay? Or Cosserà continua, in a sense. Do you want third, fourth? You add these gradients and you get more complicated contact interaction. When I said this in a conference 15 years ago, I was violently attacked, not like Victor. I was treated as a stupid boy who was telling stupid things. Okay? Now this same person is publishing papers exactly in this frame. But this is good. No, I have not written anything on this. This is Germain's paper. What we did with Pierre Serpechel is completely different. That is reproducing Cauchy argument for second gradient materials, which is another stuff. And related, but not this one. That because I'm becoming cynical, because those times I was not being too much asked.
Just to make a comment. I go back to what Gilles said before about the existence of an energy or so on. And of course there are two possible approaches. One is to start from the Lagrange, as you are doing, and to derive everything from that. And the other is just to postulate balance equations and to derive everything from this. Balance equations are the starting point of Cauchy, because the tetrahedron theorem is a consequence of balance equations.
Right.
So if you take this viewpoint, you know better than I that there is a theorem by Walter-Knoll stating that the dependence of the normal is a theorem, not an assumption. Let me finish. No, let me finish, then you will object. And this theorem is based exactly on the balance equations, nothing else. So it is coherent with the Cauchy's theorem. Okay, so the new things which came out in the last 15 years with the work of Miroslav Shihrabi and Gutin and Martins, 76 and so on, is that Cauchy's theorem is not a consequence of a balance equation, but is a consequence of a particular structure of the system of contact actions considered as a measure. So you can apply some theorems of measure theory, and what you get is not a balance equation, but what I call a pseudo-balance equations, in which you don't have body forces with it. It is just a property of the contact actions. In this sense, in this framework, you can prove Cauchy's theorem without any other things except some very acceptable assumption on the system of contact action. But at this point, if you accept Cauchy's theorem, you also have to accept the dependence on the normal. So there are two different viewpoints that I am very interested in seeing, which is the interconnection. But this is to give to the audience the information that there are also different viewpoints.
No, but so this is not a question when you have a theorem. No, it is solved. When you have a theorem like Knowles, you assume that contact actions are absolutely continuous with respect to Hausdorff measure of the surface, which means that you don't have concentrated forces on the edges.
Yeah, sure.
Okay, so you tie your hands and then you find a particular case. So Knoll theorem, which has been used by Virga and Knoll when they deal with edges forces, okay, is not valid when you relax this assumption, and the main idea for solving tetrahedron question in second and higher gradient materials is exactly the paper by Virga Knoll, where they relax the assumption of null theorem. But all this is very complicated in the sense that you need a lot of measure theory for understanding the point. Instead,
excuse me, but I agree, I don't know about edge forces, I never worked on that, so I cannot answer you. But here, you are deducing the dependence of the normal without introducing edge forces.
no, wait a second. You interrupted me exactly
1
second before the entrance in the scene of edge forces. Okay.
Anyway, just to complete your historical view, the Conservato did it before me, but in 1970 I was teaching exactly this to my students.
I know very well, because this was the old Italian school before we started to do, like in Carosone song, tubo fall'americano. They wanted to mimic Americans. If I want to mimic somebody, I like to mimic French people. This is a question of taste. Okay, so we have integral over boundary of V. You see, without Berdysevsky, we are giving you fun. Okay, tau grad S delta psi. Gilles is a very strange animal. He's American and French. He will have schizophrenic nightmares very often. Now, believe me, this is the formula is true, but you should not believe that this formula is easy. I mean, you cannot reproduce it simply by means of Leibniz rule. You need differential geometry. So, integration by parts on the surface gives you that this term here is transformed into a surface divergence of something times delta psi plus surface divergence of something without anything else. Okay? So you can apply Poincaré-Ostrogradsky theorem here, and what you get? You get an integration over the border in geometrical differential sense of the boundary of V. So this topic needs a little bit discussion. So let us first start showing that Cauchy postulate is dead. He is dead because tau is here. And if you estimate the surface divergence of the normal, you get curvature. You need, you know, the best trick is to introduce a basis for the surface, for the coordinate surfaces, and you estimate the derivatives with respect to surface coordinates. If you want to be intrinsic, you need Christoffel symbols. The representation theorem for divergence is not so easy for. So in this moment, it is better we don't spend another half an hour for this. Okay? But the important thing is that everybody sees that you are varying the normal. And the gradient of the normal is curved. Okay? So what you get, I needed to erase it. Sometimes slides are better. At the contact actions that is the part of contact interaction which can be represented in terms of measures which are absolutely continuous with respect to Hausdorff to measure for the boundary. This part of contact action is made of a second order tensor minus divergence of a third order tensor plus surface divergence of this animal. Okay, so it is a complicated animal, rather complicated. On the other hand, you... Yeah, okay, but you know, the trick is I don't want to do it because I need the blackboard, but I will show you later. The trick, the mnemotechnic trick is you write the vector field in terms of the basis, and then you do comma the surface variable, and then it works. But of course, tangent vectors are varying, so you need to estimate the derivatives of these vectors, and so you have Christoffel symbol if you want to write intrinsically. Okay. Okay. So this animal you integrate on the boundary, and now think, unfortunately, we have a trouble. Consider an edge like this. You have this normal external to this part, and this normal external to this part of the edge. So you have two normals, one, they are tangent to one part of the boundary and normal to the curve which is boundary, so the edge of the boundary. Okay? I am afraid that Poincaré should have changed the name, because boundary means something in topology, and you should use another word for the boundary of an embedded surface. If you have this surface, the boundary of this surface is this animal, if you consider it as embedded in 3D space. So it is not topologically the boundary of anything. Okay? So for avoiding misunderstanding, maybe one should change the word. So this boundary here is the boundary in the sense of Poincaré, but we force our volume to have these two boundaries coinciding. The topological boundary of V is the same as the Poincaré boundary of V. But when you have boundaries of V with edges, then the boundary of the boundary is the edge counted 2 times, because you have the edge which is the boundary of this part and the edge which is boundary of this part. They coincide as point set, but the external normals are different. Okay? So at the end you get an interesting feature, very interesting. You get tau delta psi jump normal nu. So delta psi you can get out. Okay? So you have that this animal times the outward pointing normal in the tangent plane of the boundary of your volume V, okay, estimated on one side and on the other side, times delta psi appears in your first variation. This kills the possibility of applying null theorem as recognized by Null himself in a very good paper by Virga Null, which was a starting point of my paper with Pierre Sepachet. Because if you have concentrated actions on edges, and this trivial integration by parts shows you this, then it is not true anymore that contact interactions in continua are absolutely continuous with respect to Hausdorff measure H2, with respect to area. Okay? So, after this very simple calculation, you get an important information, in my opinion. You discover several things. Antonio Di Carlo is calling this the catechism. So the catechism which has been taught in the School of Engineering, and now let us give responsibilities to French people, because of the crazy choice of Navier to simplify the previous treatment and to forget energy and simply teach final equations. You know, at the end of this integration by parts, what you get is this. You get divergence of, for instance, for Cauchy theory, divergence of T plus bulk forces, that is forces per unit volume, equal 0. And then you get Tn, I stay Lagrangian, but with the formulas I've shown you yesterday, you can be Lagrangian, so let us call Eulerian, so let us call it as equal external Lagrangian forces. Okay, you have found these equations. Then you can say, like Gilles, I don't like conservative systems. Okay, you introduce dissipation where suitable. Okay, and you attack a la Hamilton, Rayleigh, the problem. Okay, but what did Navier? He understood how difficult it was to explain to engineering students what is the first variation of energy. So he behaved by, as Plato those times, esoteric and endoteric teaching. To few people, he was teaching the right stuff. To the others, which became soon the great majority, he taught simply the final result. So he wrote the small cube contact forces on the faces, and he balanced force, and he finds this. Then, with the Maxwell pill on the boundary, he finds Sn equal external forces, and that's it. The big problem is that when you try to generalize this without a variational principle, you are lost. I was lost. I went in France and I didn't understand a single word of what was said to me. I needed to erase del star dot star and start again using a variational approach. Edge forces, and this is another topic. When should I stop? I forgot completely. Half past, I have another half an hour. Edge forces arise in continua, which are the macroscopic counterpart of microscopic, highly inhomogeneous systems. So if you have the system which Gilles was showing us yesterday, you have inclusions with a very strong or very weak Young modulus inside a surrounding region with very so you have a really dishomogeneous situation at the microscopic level. Then you calculate the average and gradients pop out and you are lost. In the case of porous media, you have interconnected channels filled with fluid. So think about a fluid which is this. He had drunk 3 glasses of wine, but Victor said, this I buy. So I can tell you that he agrees with this reasoning. If you have a fluid nearly incompressible in a network of channels of pores, you push a little bit the fluid, far distance pores will be affected. So you have rigidities which are varying in a non-local, highly non-homogeneous way. Or think about the problem which I tried maybe too quickly to describe you last time, that one of consolidation. You know, this problem of consolidation is a nightmare for geotechnical engineers, because they write final formulas and learn them by heart usually, so they do not know, they cannot explain you from where they got. So I needed to reconstruct this in the original books of bio. If you have here pores and this boundary is free, permeable to fluid flow, you push here, what happens? The fluid is flowing out, the pores are shrinking. What are you deforming? Nothing. The fluid is coming out, the pore is shrinked. So there is few energy, deformation energy, in shrinking this pore. Mass is reorganizing, filling the holes. In this situation, and this already again was bought by Victor, in this situation, second gradient here in the deformation energy plays a relevant role. So whenever, this is a sure statement, whenever you have some boundary layers where highly dishomogeneous physical properties must be modeled at a macroscopic level, there for sure you need second gradient theories. Let me tell you how I started. I changed completely my plan, but I think that it is better to give you all details for one.
Can I ask you a question?
Yes.
Do you mind writing the equation that just so that we know, because it's hard to, I mean, maybe they're in the notes, but since I never received your notes or anybody's notes.
Then you have double forces.
What is capital C?
He's good.
Capital C is this third order tensor, this one.
Okay.
Okay. And then you have, but this is not ended, because you have edge boundary conditions. So Cn tau at the edge equal force per unit line. And then you have double force condition, which is this one. So it is N Cn equal tau external. And as usual, now let's see this point. By the way, these things you write more or less in the same way without the outbreaks of temper of Neapolitan origin. You find written in the lecture notes with exactly the same details, but what people are always complaining is, who gives you this boundary condition? Now, the question was posed exactly to Euler when he deduced the equation of Elastica. Who gives you this strange animal which is expending power on the rotation? He called it moment or couple. Okay? Now, Paul Germain, in my opinion, was cleverly gathering results which were all around. But what he did in a very clever way, he gave names which are suggestive of physical reality. He called this double force. It is an action which is working on the normal derivative of velocity. The skew part of this reduces to couples. So you get cossera continua as a particular case. But you have opening or closing actions on the boundaries. You can interpret this as capillary forces, for instance. If you have a drop, everybody could see a drop which is not falling because it is glued to a plane, an horizontal plane. You have here edges, and here you have edge forces, and you have here double forces. You call them wettability in this context. By the way, Gilles Desgennes got a Nobel Prize for having understood this kind of phenomena and their description. Okay? Now I tell you something else. Let us, I erase this, but I will need this. I started my research in a completely different field. I wanted to study the growth of a drop of a liquid surrounded by its vapor. Now think about this problem. Everybody knows Laplace formula, okay? I was young and my professor in Naples was not strong enough, so we published papers only on the local journal, Ricerche di Matematica, okay? Which is not the journal of École Polytechnique, so nobody read these papers. If you try to model this with a perfect fluid, so the interface is not concentrated on a surface, it is thick. Okay, so actually you have an interfacial region. This you can think. Now you apply minus grad P equals 0, Euler equation of equilibrium of a fluid. What you discover? P constant. How can you get then jump of P equal 1 over radius of the droplet times a constant which you call surface tension? I spent a lot of time trying to understand this point until I met Henri Gouin in Marseille and Pierre Seppecher in Toulon, and we wrote 2 or 3 papers in French journals, so much better than the others. We proved that in this region gradients are important.
This is a paper by Hazard.
Yeah. Yeah, but the numerical estimation of the surface tension with the variation of the radius, we wrote in this paper with Henri Guin. And we estimated also the thickness. You know, it is very important from the experimental point of view. If you have the plot of gamma surface tension as a function of the radius, you discover an interesting phenomenon. You have a bump like this. For very small radiuses, you have no mass and the interface. You will say the drop is only interface. So you have a very low surface tension. You reach a maximum, and then you go down and you reach the standard constant value of gamma. Okay, so imagine you want to deduce this constitutive equation for droplets having a continuous theory like Euler theory. Now, the ingredients of this physical problem are: you have a characteristic length, the thickness of the interface. You have a region where you have high gradients of density. So, instead of writing minus grad P, you can write minus grad of P of rho minus Laplacian lambda Laplacian of rho equals 0. This animal is very difficult to integrate, and you need to use tricks of numerical calculus analysis for finding the profiles, because it is rather unstable as a profile. So you need a neat numerical treatment, and you find the profile rho. You define the interface where gradient of rho is big. You integrate W of rho, grad rho in that thick region, and you find surface tension. So I tell you this for giving you instructions. If you have a heterogeneous system with sharp variations of mechanical properties at a microscopic level, so for instance, porous medium at the boundary, porous medium when you have a jump of material properties, then, or in plasticity, when you are at the border of the region where this was done by Aifantis, you have a region where plastic phenomena are starting, and outside this region you have elastic behavior. And you want to understand what happens at the interface between plastic region and elastic region. Everywhere where you have, in every situation, when you have these sharp variations at a microscopic level, then you need second gradient, or higher gradients maybe. Okay? Okay, so maybe I stop here. Okay? Thanks.